Hi there, Dr. Herath here. So we're going to look at how to solve problems using pH and pKa, autoionization of water, and pH scale, weak acid dissociation, and we'll solve a problem or two. In this diagram, I want to look at the central water molecule. You see O to the H polar covalent bond. If this bond is broken, giving the both electrons to the oxygen, which is electronegative, and see the attraction hydrogen bonding, the weak intermolecular forces will keep this proton detached onto this free water molecule. Think about that. Now also I want to compare water to methane, and you can list these characteristics side by side, and eventually we want to understand in the pKa scale it says 16 and 50. These numbers are indicating simply how much base power needs to detach this proton. So let's see whether we can understand that. Now if I start with a single water molecule, and we can break this bond and generate proton and hydroxides. Now there are no single water molecules, there are gazillions of water molecules. So therefore, due to the thermal energy, they colloid each other and generate hydronium and hydroxides, right? Numerically, the proton number and the hydronium should be the same, right? Now, how many? That would be 10 million to 1 ionized from molecules to the ions, right? Now, this is a big number, but we can write it as 1 over 10 million as 10 to the negative 7. To simplify more, I can take the negative log of the hydronium concentration, 7. That is pH 7. Now we can see hydronium to hydroxide is equal amount, so that's neutral. So let's see, these are the formulas we're going to use when we solve the problems. So we're going to skip this one. Yes, we want to be familiar with this scale here. So look at this one here. pH 0 to 1 area, lot of protons, that means acidic, but trace amount of hydroxides. Go to 13 to 14 in the pH scale, lot of hydroxide, trace amount of proton, right? And in the center, 7 equal amount, just like the way we saw when the water is split, you have same number of hydronium to hydroxides, right? Once you're familiar with doing math with pH and hydronium, we're going to learn about pOH and hydroxide concentrations as well. Now, my other question is, do you speak arrow? So let's look at this one here. HCl is a strong acid, and then look at the arrow, one arrow, single arrow, dissociate 100% fully. So that's the nature of strong acids. Not much of math to do with it. But let's look at the acetic acid here and look at the arrow here. That's an equilibrium arrow. So it's partial dissociation. Now, in order to understand this one better, I would say any weak acid, I can think anion with a dissociable proton. We also can call this one is a monoprotic weak acid, right? Reacts in the same fashion. Now, even better way to solve problems is take the generic formula of HA, dissociable proton, and A minus A, and reacting with water, giving rise to A minus and hydrogen. Now the question, where is Ka and pKa? So let's look at here. So if I remind you a previous chunk, in equilibrium you learned equilibrium KEQ, KC, KP is product over reactants when the forward rate is same as backward rate, right, at equilibrium. Now, in this type of reaction, if I have hydronium here, I can actually write a Ka. If I have hydroxide here, I can actually write a Kb. So that's the difference. Now, let's look at the Ka expression. In this one, this slide, I'm showing you, you need this slide many times. So I'm going to show you the generic formula for any weak acid. And then initially we can write molarity is given, and water is not a concern because it's a liquid. And then very beginning, nothing and nothing. But the change based on the stoichiometric ratio 1 to 1 to 1 to 1. So we're going to use minus x loose and get x and x. Now at the equilibrium, m minus x and 0 plus x and so on, right? We're going to consider, without doing the calculation for 5% rule, we can neglect this one as negligible or 0. right? Now we can plug into the Ka, product over reactants, and we will get a number. Now, whereas pKa, this number is bigger and not very comfortable to use it, so we're going to take the negative log Ka value. Okay, let's solve some problems. Let's look at how to find pH when you are given the proton concentration. In this case, hydronium or proton concentration is given, and we're going to use pH is negative log proton concentration formula. So negative log, go to the function and find log, negative log, within brackets, proton or hydronium concentration, in this case 0.05, that gives me 1.30 pH. So let's write that one here, 1.30, and then we for the beginner's task, those are simple, straightforward questions to do. And let's take another one. Let's say 5.4, 10 to the negative 5. So that's how usually you see in the scientific writing. So the molarity is given like that. So again, it's the same thing though. So it's just like this one, 0.05, but you're going to replace what is within brackets with the scientific writing of the molarity. So you just plug in 5.4, 10 to the negative 5. That's the molarity of the proton. So that'll give you the relevant pH because you're using negative log proton concentration, right? Okay, so keep practicing that one. After that, we can do the ice tables. In this question, you are given a methanoic acid, a weak acid, HA, the molarity you're looking for, but you're given pH and Ka. So in any of these questions, ice table related ones, we're going to do the same thing. HA going to H plus and A minus, and ice table, and initially we have M molarity and 0, 0, change minus x, 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 and equilibrium M minus x. Here this x is negligible, 0, and products have protons. I'm going to write a Ka, product over reactants. Now we can say it is x squared over M, right? So because H plus and A minus is x and x. Now to find x, you're going to use pH, given pH. So H plus is x. So H plus concentration is 10 to the negative pH. So you're going to use the calculator. 10 to the negative pH value, which is 3.27, will give you the x, the molarity of protons. In this case, 5.37, 10 to the negative 4 molarity, right? So now we can substitute the x squared with that one. So let's rewrite it. Ka is x squared over M. You do the cross multiplication to isolate M, the molarity, and plug in the numbers. 5.37, 10 to the negative 4 squared divided by the Ka. So x squared over Ka. Add the values, use the calculator to get the molarity, right? In this case, we get the molarity 1.6, 10 to the negative 3 moles per liter. See whether you get it. So next question, calculate the Ka for carbolic acid, and molarity given, pH given. Now we are looking for Ka, but we're going to use the same thing, ice table. So here pH will lead you to get the x value, proton concentration. Again, Ha, any weak acid, H plus A minus, and then molarity is given 0.06, 0, 0, and then similarly you do the problem, right? Write Ka and plug in the numbers, and you're going to get the Ka. Now the last thing, the challenger question. This one I'm just trying to show you to make sense of the Henderson-Hasselbalch equation. In this case, weak acid is sitting with its sodium salt, and the sodium has no value. Let's say I have 1:1 Ha to A minus, so that means 1:1 is log 1, that is 0. So that means based on the Henderson-Hasselbalch here, that would be pH is pKa. Let's say I have more base, double the base. That will give me log 2. Log 2 is 0.30. That means pH becomes 5.04. So that means you add more base, you get a higher pH buffer, right? Let's go the other way around. So you add more acid, twice acid. So that will give me log half, which is negative 0.30. pH would be 4.44. You see how the Henderson-Hasselbalch is used to find the pH.